It's a pleasure to have a chance to talk with you today. I apologize for not being able to attend in person given the pandemic. However, I'm very pleased to have a chance to convey the results of the verification work, and a warm felt thank you to all the competitors and our stakeholders and partners in the Ag Results project. I am Bill Salas, the President and Chief Science at Applied Geosolutions. We are the lead verification team and have worked very closely with Dr. Trin and his team at IAE for the verification process, as well as with CPP on the collection of verification data to quantify the outcomes of the program. Again, I apologize for not attending. I wish you all the best, and will now summarize the steps in the verification and the overall outcomes. The overall role of the verification team is to track adoption of the Ag Results technologies, verify that the management practices were implemented according to the technologies that were tested in phase 1, and then use all this information to try to quantify greenhouse gas impacts of these new technologies and also the impact on overall yields. So as I mentioned earlier, IAE and CPP are key team members in this whole process. Applied Geosolutions did the DNC modeling and the Horizon modeling to quantify greenhouse gas outcomes and yield increases. The overall approach for verification for phase 2 was to use these modeling tools that I'll talk about in a moment to basically model the outcomes of the various competitors' technologies with individual smallholding farmers. The modeling was based on the management practices entered in the Ag Results AVERP WebGIS management system that enables the competitors and their stakeholders to quantify and report exactly how each rice field was managed, starting with when the fields were planted, how the transplanting occurred, fertilizer management, irrigation and water management, and then final dates of harvest. So to quantify the net greenhouse gas emission reductions, we take that actual management system to model the greenhouse gas outcomes, but then also for that same field, model what we call the counterfactual baseline, which is typical agronomic practices for rice production in Taibin. And then we use the difference between the modeled greenhouse gas emissions for the competitor technology and the counterfactual baseline to estimate net greenhouse gas impacts of that technology. We do the same thing using the DNC Horizon model for quantifying the yield outcomes associated with the implementer's technology relative to what would have occurred under baseline management and baseline varieties. In addition, we collected thousands of field observations to verify that the technologies were implemented correctly. So this includes going out and verification that the right varieties were planted, the right planting density was used, the right type and amount of fertilizer on the correct days was applied. We also try to track the impact of irrigation management and flooding and draining of fields, recognizing that weather patterns can have a significant impact on the efficacy or success of a drain technology. These field data are then used to estimate percent compliance on a competitor by competitor basis and a cropping season basis. I will now provide a little bit of background on the quantification tools, the models that we use to estimate the greenhouse gas and yield impacts of the technologies. In phase 1, in collaboration with IAE and Dr. Trin's team, greenhouse gas fluxes were measured from the various technologies and the associated baseline. Those measurements were used to evaluate the technologies for phase 2, as well as to validate and calibrate the DNC model for estimating greenhouse gas emissions from different agronomic practices in Taibin. The figure on the left shows sort of typical validation of the DNC model for estimating methane emissions from rice. And I'd like to sort of note that this approach of using DNC to model actual greenhouse gas emissions from a technology and then comparing it to a counterfactual baseline to estimate the net impact of the technology is a common approach used in carbon and ecosystem service markets globally. And D&DC has been used pretty extensively for serving those markets. The yield outcomes of the program were quantified based on using an integrated model that takes sort of the science of the ORISA model and integrates it in the D&DC platform to estimate the agronomic impacts of different management practices on yields based on various varieties. So in phase one, we did a calibration for all the phase one varieties. That's the panel in the middle that shows high correspondence between measured and modeled yields, giving us confidence that the model results are reasonable. And then in phase two, we continued to collect some additional data to check that calibration and revalidate the model, especially for certain varieties that were used for the baseline calculations. And that's the figure on the right shows calibration and validation results, expressing measured yields from field observations compared to modeled yield estimates. Again, pretty high correspondence between measured and modeled, giving us confidence that the model is performing well. But as you know from these figures in general, models are models. The key piece for this program is to demonstrate that there's not a strong bias in the model and that we can generally model the range in outcomes in terms of yields and greenhouse gas emission reductions. And so based on historic use of D&DC and the CalVal work we did under Ag Results, we're confident that the model is performing reasonably well and suited for the use to sort of quantify the outcomes of phase two. We evaluated the technology implementation success in sort of two different levels. One is what we refer to as compliance verification. This is where how the individual SHFs implemented technologies. Do they follow the fertilizer guidelines of the technology? Do they follow the crop variety and planting aspects of each technology? And that's something that each individual farmer can control. So we refer to that as compliance verification. And in essence, it's an estimate of the percentage of the frequency of correct implementation of the technology. The other verification workflow is to track the success of the drains, recognizing that while an individual smallholder farmer may try to drain a field, there may be weather conditions that prevent that from being successful. So we tracked the success of drains and also use that information to estimate what would have happened in the counterfactual baseline, recognizing that weather might have impacted the success of baseline drains. So these tables summarize the overall success in phase two. As you'll see, drains, especially in the summer season, were somewhat difficult to successfully implement. And in the summer season, that's really hampered by heavy rains. In terms of implementation of the overall technologies, I think the technology implementation was highly successful. In the first two crops of phase two, average implementation success was about 90%. And then that decreased slightly in the last two cropping seasons as the program scaled. But overall, pretty strong compliance, especially in the first two cropping seasons of phase two. This table shows the overall results for each of the phase two cropping seasons by competitor. Results are shown by greenhouse gas emission reductions relative to the baseline, as well as yield increases relative to the baseline. And the results are shown on a percent and a magnitude basis in this table. And overarching sort of take-home messages are the first half of phase two, the first two cropping seasons, there was high success in terms of emission reductions of greenhouse gas emissions. The implementation of the technologies led to, I would consider, pretty significant reductions in greenhouse gas emissions. In the latter part of phase 2, we see emission reductions went down relative to the first 2 cropping seasons, and that's due in part, I think, to a drop in overall compliance as the program scaled. As we saw significant increases in the number of smallholder farmers the last 2 cropping seasons. So as far as the yield outcomes, again, during the first 2 cropping seasons in phase 2, we saw significant yield increases relative to the counterfactual baseline, and the technologies were all quite successful. The last 2 cropping seasons, we saw more varied success across the technologies and from spring 2020 season to the summer 2020 season. Again, in those last 2 cropping seasons, we basically see an insignificant change in yields relative to the counterfactual baseline. This slide presents the results of the actual greenhouse gas mitigation relative to the potential. By potential mitigation, here I mean that had each of the competitors' technologies been successfully implemented by each smallholder farmer on each field in the program, what would have been the total greenhouse gas emission reductions for the program relative to the baseline? And so here I present the results on a competitor by competitor basis, and you'll see a few things sort of stand out. 2 of the technologies had potential for greenhouse gas mitigation, illustrated here as competitor 1 and competitor 2, and that mitigation potential was smaller than the other 2 technologies, and that's driven by 2 factors. One is the technology itself, and the other is the size of the scaling in terms of the number of fields that implement that technology. As you scale to larger hectares, you have a greater potential for greenhouse gas mitigation. The other aspect of this graph that I want to focus on is the actual efficacy of the actual mitigation relative to the potential. For 2 of the competitors, there was actually relatively small or no greenhouse gas emission reduction in phase 2 relative to the mitigation of, or relative to the baseline emissions. But we do see for the 2 technologies that had the highest potential that we saw significant emission reductions. These emission reductions are expressed in tons of CO2 equivalent, so showing that the program had significant potential, especially 2 of the technologies for 2 of the competitors, and achieved about a 45% reduction relative to the potential. So that's driven in part by the efficacy of implementing the technologies, so the percent compliance, as well as the difficulty in successful drains during heavy rains. This slide shows the results of the SHF verification and repeat use verification, as well as a short summary of the outcomes in terms of yield increases and greenhouse gas emission reductions across the 4 phase 2 cropping seasons. The table on the top of the slide illustrates the number of SHFs in the program. Overall, there was an enrollment of close to 39,000 smallholder farmers across the 4 cropping seasons. Of those, roughly 32,000 or 84% actually participated in the program. We'll also see in the top table that in addition to significant scaling of SHFs from one cropping season to the next, we saw continued expansion of the cropping area across the 4 crops in phase 2, where in crop 4, or the summer of 2020, the AVERP technologies were implemented on almost 2,400 hectares in Tai Binh. The middle table shows the repeat use metric. Just to review, the repeat use metric is a number of smallholder farmers that continue to stay in the program from one cropping season to the next and implement the same technology. Again, you see increases in repeat use participation by the smallholder farmers, indicating there's strong interest in the technologies, and that increase, reached approximately 25 or 30% rather by crop 4. The bottom table highlights overall outcomes of the program based on our modeling compared to what would have happened in Taibin under the baseline scenario. Yields were increased by roughly 1,000 tons, which is fairly significant. Greenhouse gas emissions were reduced by 2,300 tons of CO2 equivalent during the program. So as the program scaled, there were positive yield and greenhouse gas mitigation benefits achieved by each of the programs and on a season-by-season basis. Now that we've summarized the results from the 4 crops in Phase 2, I want to review and present the final results in terms of the grand prize scoring metrics and prize calculations. To summarize, each competitor's final score is a combination of their success relative to the other competitors in terms of reducing greenhouse gas emissions, increasing yields, enrollment of smallholder farmers, and getting smallholder farmers to continue into repeat use of the technologies. So this formula here shows the relative weights of each metric. The most important metric in this scoring system is the number of smallholder farmers reached. That's weighted as 40% of your score. The greenhouse gas, yield, and repeat use outcomes are all equally weighted at 20% each individually. To sort of review on how we calculate a competitor's score, for example, the greenhouse gas score, is we sum up for a given competitor the total greenhouse gas emissions during the Phase 2 and divide it by the total greenhouse gas emission reductions from all 4 competitors in Phase 2. So each individual score indicated by a sub C here is a fraction score, meaning what fraction of the total beneficial outcomes of the program did that competitor achieve on greenhouse gas emission reductions. We do the same for yield. We sum up all of the yield increases for Phase 2, and for each competitor, we take their yield increase divided by that sum to create their score for the yield metric. The same is done for smallholder farmers. We have the total number of smallholder farmers in Phase 2. Each competitor's number of smallholder farmers that were successfully enrolled is divided by that total to create the SHF score for this, the SHF metric for the final prize score. And the repeat use metric is calculated in a similar fashion by summing up the total repeat use by SHFs in Phase 2, and each individual competitor's score is their SHF divided by the overarching number of SHFs that repeated to use the technology in Phase 2. Moving on to the next slide, this shows the individual scores for each of the competitors. It's a bit complicated. So when we do the greenhouse gas and SHF verification and yield estimation, it's based on our verification sampling of success of various events in terms of the technologies, as well as how well individual fields were able to drain their success. So we have a sample estimate of the success of the entire program, but that sample gives us some estimate of uncertainty. So if you look at the figure on the left, each colored box and whisper plot is a different competitor and illustrates our range and uncertainty in their estimate of total greenhouse gas emissions reduction for Phase 2. Again, the next panel shows the yield increase Again, there's some estimate of uncertainty because we don't know exactly for every field and every component of a technology was it implemented correctly. So we use our verification sample to estimate percent compliance. We then apply that percent compliance to the modeled yields to come up with this range and outcomes. What you'll see from the first two panels is one of the competitors was not successful in reducing greenhouse gas emissions. Another competitor had very minimal reductions, but two were quite successful and accounted for the majority of the program reduction. So the y-axis on these panels is the metric score for each of the different metrics. The yield panel illustrates that one of the growers that actually had difficulty with greenhouse gas mitigation actually had significant increases in yield relative to the other competitors, accounting for roughly 60% of the overall yield increase. The middle panel shows the relative fractions of overall number of smallholder farmers throughout phase 2. Again, you see significant differences across competitors in terms of the fractions of the total number of SHFs that they enrolled in the program. The panel on the right, under overall repeat, that is the repeat use metric. And again, something that sort of stands out is one of the competitors was highly successful in getting the smallholder farmers to continue to use the technology and accounted for roughly 60% of the overall repeat use metric. So you see those four metric outcomes, and then when you combine all of these metrics by the weights that we discussed in the previous slide, you now get an overall score, and it's a relative scoring system from one competitor to the next. And you see that clearly from these results, one of the competitor was clearly the most successful. There was a second competitor that was clearly was second in terms of overall performance, and then again a third competitor that was clearly coming in third place, and then lastly the fourth competitor was significantly behind the other competitors when evaluated on the scoring metric integrating greenhouse gas emission reductions, yield increases, SHF, and repeat use metrics. So this is the graphical representation of the score and how we integrate all of the metrics together to come up with a single final score for each competitor. This slide summarizes the prizes associated with the grand prize. As AgResults has established, the first place prize will receive an award of $750,000 US. Second place will receive a $400,000 grand prize, and third place will receive a $200,000 grand prize. So the figure here is illustrating the final scores for each of the competitors, but showing the uncertainty in that each individual competitor scores is a range. And if you recall, during the other phase 2 cropping seasons, the seasonal prizes were based on these similar type scoring system, but if there was an overlap between competitors on their final score, we did a proportional assignment of the first, second, and third place prizes to reflect the uncertainty in the quantification, such that if there was an overlap in scores between two competitors, a portion of the prizes would be shared by those competitors. What we see here for the grand prize is we don't have an overlap in the final scores associated with the uncertainty of each competitor's final grand prize scores. So as a result, there will be no sharing of prizes. A first, second, and third place prize will be awarded, and a fourth competitor will actually not be receiving a grand prize because their overall performance in phase 2 across the 4 cropping seasons was clearly the performance was not as good as the other competitors. So there will be 3 grand prize awards provided during the ceremony later today. I'd like to wrap up the brief presentation on the overarching approach for the verification and explanation of the outcomes and how the outcomes are used to calculate the grand prize. It's again unfortunate that I was unable to attend in person. I want to thank everyone in the Ag Results AVERP program, all the competitors, their stakeholders. Sincere thank you to SNV and TUHA, the project management team. They've been a pleasure to work with throughout this program, and also special thanks to other members of the verification team and at IAE and CPP. And I think, overall, it was a very successful program. I want to congratulate everyone for their efforts, and wishing everyone the best. Enjoy the rest of the award ceremony and festivities for this closing ceremony. And my hope is to see you all again one day. Thank you.